Hi, I'm Herb Gross, and welcome to Lecture 15 in Gateways to Algebra, where today we begin the first of a two-part series on looking at what we call linear equations. We've already done part of this. We may not have given it an official name, but we've already started it. Let's go back to something that we did very, very early in our introductory lectures. Let's just take a very simple equation. Let's say 3x plus 2 equals 29. Let's just start with that one. 3x plus 2 equals 29. Now remember how we played this game. What we said, the name of the game was isolate the x. Without parentheses, we assume that multiplication is done before addition. The parentheses are protecting the x. We said what? To unblock the parentheses, we have to get rid of the 2. Since the 2 is being added, to get rid of it, we have to subtract it. If we subtract 2 from one side, we also have to subtract 2 from the other side to keep the equation balanced. So this leaves us with what? 3x on the left. 29 minus 2 is 27. We're left with 3x equals 27. By the way, that's the traditional way that I was taught algebra. I would like to show you at this time what we mean in terms of the so-called rules of the game, the axiomatic approach to algebra. Remember, we listed like 14 or 15 rules. And see, the technical way, if a person says, I don't see how you can subtract the negative 2, subtract 2 from both sides, the way you say this is what? Equals added to equal. If these two expressions are equal, then I can add negative 2 to both sides. By the associative property, I can regroup the 2 here with the negative 2 here. What's the purpose of doing that? Because one of our rules of the game said that any number plus its opposite was 0. So this side became 3x plus 0. That's still 27 over here because 29 plus negative 2 is 27. One of the properties that we had, one of the rules, was that adding 0 doesn't change anything, and therefore 3x plus 0 is the same as 3x. Now the important thing is, we don't have to go through this every single time this way. All I want you to see is that whenever we do an intuitive demonstration, and somebody says, this is all you have to do, if everybody's willing to accept it, that's fine. If the person is not willing to accept it, then you have to go through the rules of the game. I mean, let's just practice that one more time. For example, suppose we're down to 3x equals 27. The colloquial way of doing this was to simply say, look, we want to get the x by itself. Since the x is being multiplied by 3, we'll divide by 3 to get rid of it. If we divide by 3 on one side, we have to divide by 3 on the other side, and 27 divided by 3 is 9. The axiomatic approach is to say what? We eventually want to get rid of the 3. We know that there exists a number called 1/3, such that 1/3 times 3 gives you 1. So the strategy becomes what? Multiply both sides of this equation by 1/3. Then by the associative property of multiplication, you can regroup this so the 1/3 and the 3 are together. By definition of 1/3, the multiplicative inverse property, 1/3 times 3 is 1. So the left-hand side is now 1x. And since one of our rules says that multiplying by 1 doesn't change anything, remember what we said, 1 is the multiplicative identity, 1 times x is the same as x. So in other words, if somebody challenged us, these steps together justify saying, let's divide both sides by 3. And so that's how we're going to keep the spirit of the game. So in other words, let's just summarize now what we've done. See, this didn't have to be a 3. This could have been any constant multiplying the x. This didn't have to be a 2. This could have been any number over here. And similarly, the 29 could have been any number. In other words, the general form would have said what? Start with x, multiply by some constant m, add on b, and the answer is going to be c. See? In other words, this would be now called a linear equation. All right? And the object of the game is to solve for x. Now, what's the summary? Reviewing what we did, the first thing is this is being treated as one number, so we want to get rid of the b. The b is being added. To undo adding the b, we subtract it. And if we don't like subtraction, we can say what? Add the opposite. In any event, when we do this, we subtract b from both sides. What's left on the left-hand side is m times x. On the right-hand side is c minus b. And the only difference is, remember, if c had been 29, for example, and b had been 2, now instead of writing c minus b, you just would have written 27, because 29 minus 2 is 27. The only problem you have to get used to is when you're working with letters of the alphabet, to represent numbers. When you subtract b from c, you can only represent that as c minus b because any other numerical value will depend on what you've chosen for c and b. We're now down to this stage over here. We now want to do what? Solve for x by itself. As long as m is not 0. In fact, if m was 0, you wouldn't have a problem here. You would have just b equals c, and that would only be true if you chose b and c to be the same thing. But if m is not 0, what can we do? We can always divide by a non-zero number, so we can divide this side by m. If we divide this side by m, we also have to divide this side by m. So if we do that, this cancels out, and x is equal to c minus b over m. In fact, what I'd like to do here is a little diversion, and just do this a little bit more generally, because we started to do this last time, and I didn't have time to finish this. See, what we have over here is the form y equals mx plus b. And this thing is geared so that if you start with x and you want to find y, it's a straightforward arithmetic problem. It says what? Start with x, multiply by m, add b, and the answer is y. The trickier part happens if somebody says, we'll give you the value of y and now solve for the x value. In other words, suppose I said to you, rewrite this so that we isolate x. And the way this would go is what? The x is being multiplied by the m first, so I have to unblock the parentheses. The b is blocking the parentheses. Since the b is being added, I unblock it by subtracting. If I subtract b from one side, I also have to subtract b from the other side. Now I want to get x by itself. It's being multiplied by m. To undo that, I want to divide that by m. So x is going to have to be y minus b over m. And what I want you to notice is, if you look at this, and if you look at this, they're really quite different. But what they have in common is that these are two different ways of expressing the same relationship. And what you do is, if you're given the value of x and you want to find y, in other words, if you're given the input and you want to find the output, this is the form to use. But if you're given the output and you want to reconstruct the input, this is the form that you use. In fact, you know, we were doing that with Fahrenheit and Celsius, and I didn't get far enough to show you that, but let me just go back to that now. See, what did we show last time about how you transformed Fahrenheit into Celsius? We said what? You start with the Fahrenheit, you subtract 32, then you multiply by 5/9, and the answer is the Celsius temperature. Remember, we started with 77, we subtracted 32, that gave us 45. Then we took 5/9 of the 45, and that gave us 25. So that 77 degrees Fahrenheit was 25 degrees Celsius. Now the problem was, what if you had started with the Celsius? Well, if you started with the Celsius and you were reversing these steps, to undo multiplying by 5, you would do what? To undo multiplying by 5/9, you would divide by 5/9, but dividing by 5/9 is the same as multiplying by 9/5. To undo subtracting 32, you would add 32, okay? And therefore, what would happen over here? Reading from the bottom to the top, you would start with c, multiply by 9/5, and then add 32. Now, these two formulas look different, but they're simply what? Two different expressions to tell you the same relationship. This relationship is the one to use in the easiest way if you're given the value of f and you want to find the value of c. But if you're given the value of c and want to find the value of f, this is the better one to use. But both of these are what? Formulas, and one of them is devised to be simpler if you're given the input and want to find the output, and the other one is set up so that if you're given the output and want to find the input, this is the way to do this. I just wanted you to see that particular picture. Now, what happens next in mathematics is that we often proceed to more difficult situations by generalizing simpler situations. The equation 3x plus 2 equals 29, if I wanted to write this so it would look more complicated, isn't 0 times any number still 0? Couldn't I look at this as being 0 times x plus 29? You might say, why would you want to do that? Why would you want to do that? Well, what I want to try to show you is that in general, we've been dealing with what? The left-hand side being of the form mx plus b, but the right-hand side is just plain old c. I want to show you that we can equate these things when both sides have the mx plus b form. And that in fact, when we were dealing with the right-hand side being 29, that was a special form of mx plus b, where b played the role of 29, but 0 played the role of m. So let's just generalize this problem. Suppose instead of 3x plus 2 equaling 29, we were given 3x plus 2 equals 2x plus 29. Okay? Now, the way to solve this problem is basically to reduce this problem to a simpler problem. What kind of problem are we already able to do this way? We already know how to solve the problem if the x is only on one side of the equation. Well, for example, what's the 3x doing over here? It's being added, isn't it? So if I subtracted 3x from both sides of the equation, it would be gone from this side, but it would now only be on this side. I could also have said, look, the 2x is being added to the 29. To undo adding 2x, I can subtract 2x. And if I subtract 2x from one side, I'll also subtract 2x from the other side. My feeling is, see, I like to avoid negative numbers if I can, because there's just enough things that happen with negative numbers that can make you make careless mistakes. See, if I elect to subtract 3x from both sides of this equation, the left-hand side becomes 2. 2x minus 3x is negative x. And you see what's happened over here is I now have an equation that involves negative x rather than positive x. So when I finally solve this equation, I have to remember I've found the opposite of x and hence have to take the opposite of the opposite to find x. My feeling has always been, in this step, always decide to subtract the smaller amount from the greater amount so that the result will always be positive. In other words, to apply that to this problem, the way I would look at this is, I say, if the x's weren't on this side of the equation, I would be back to the same kind of a problem I was tackling before. How do I get rid of the x's? You can't just get rid of something. It has to be according to the rules of the game. So one of the things I could do here is to say what? Since the 2x is being added to the 29, to undo adding 2x, I'll subtract 2x. But if I subtract 2x from one side, I also have to subtract 2x from the other side. So if I subtract 2x from 3x, I'm left with 1x. I don't have to put the 1 in here, but I just put it in here to remind you that 3 minus 2 is 1. I'm going to use the rule that says 1 times anything gives you the same thing back again, so I will in the next step replace 1x by x, but that's not the real serious issue over here. The thing I'm going to do is what? Subtract 2x from both sides. I'm left with 1x plus 2 on this side. The purpose for subtracting the 2x was to get rid of the x's on the right-hand side, so I'm left with 29 on the right-hand side. And so what am I left with? X plus 2 equals 29. And here's a very good place to pause. Because what I want to show you is, suppose you were very nervous about algebra and your life depended on solving one of these two equations. 3x plus 2 equals 2x plus 29, or x plus 2 equals 29. Notice, I think, that you would rather solve this one than this one. But the important thing is that these two equations are equivalent. That these two equations say the same thing in a different form. More importantly, any solution to this equation will be a solution of this equation and vice versa. The thing is that once we're down to this step over here, we now have reduced an unfamiliar problem to a more familiar problem. How do we solve this problem? Just subtract 2 from both sides. See, because I want to get x by itself. To undo adding 2, I'll subtract 2. That will leave me with x on this side. If I subtract 2 from 29, I get 27. And by the way, one more thing I'd like to teach you is some people will call this the answer. No, this is actually an equation. It says, for what value of x will x equal 27? It just happens that this is an easy equation to solve. It's like saying, what's the color of Paul Revere's white horse? You see, here it's kind of obvious what the x stands for. Is it that obvious up here? No. But the beauty of algebra, the thing that makes this a human endeavor, is that this complicated statement has been reduced by what? A very trivial equation that can be solved by sight. And yet it's what? The same as the answer to the more complicated problem. In fact, you don't have to take my word for this. The nice thing about algebra is, if you've got the right answer, what should happen? When you check this, it should work. In other words, what this says is, if you replace x by 27 every place it appears, this should be a true statement. Let's see if it is. I'll replace x by 27 here. I'll replace x by 27 here. This means multiply. 3 times 27 is 81. 81 plus 2 is 83. The 27 replacing the x over here. 2 times 27 is 54. 54 plus 29, also 83. So it works. By the way, what's even more important about the algebra is that not only did we show that this works, we've also shown that it's the only time we'll get the right answer. In other words, what this said is, look, if this is true, then this has to be true. And if this is true, this has to be true. And if this is true, this has to be true. Well, what does that say in logic? It says if this is not true, then this won't be true. See, we've not only shown that 27 works, but we've also shown, which you can't do by trial and error, is that if x is not 27, then 3x plus 2 can never equal 2x plus 29. So in other words, this will be an equality only when x equals 27, in which case both sides will be 83. Now let's just pause for a moment to ask, so what? You see, if you're an algebra buff, you say, wow, this is nice. If you're into language and like paraphrasing, you're going to say, isn't that a nice example? I never realized that algebra was also a language. But if you're taking this course against your will and have to take it, a very natural question is to say, where am I ever going to use this? Where will it ever come up? Well, I won't give you real difficult examples to see this with, because after all, if you don't like math, any difficult application of math is going to make you feel even more ill at ease. And if you do like math, you'll think of these examples by yourself. So let's take a very simple example in real life where to solve that problem, you have to solve the equation that we just dealt with. Let's suppose you're dealing with Christmas time, and you're going to shop to buy friends presents, and you happen to like a particular catalog that's selling cheese and other fine things, and you have two catalogs. Catalog A says $3 a pound plus $2 for shipping and handling. Catalog B is a completely different situation. Catalog B says it's only $2 a pound, but I'm going to charge you $29 for shipping and handling. Now, how could that happen? Well, maybe to get the price down from $3 a pound to $2 a pound, you have to do a lot of work, and therefore you expect to be paid for the time it took you to do this. So at any rate, here are these two catalogs. One catalog says $3 a pound plus $2 for shipping and handling. The other one says $2 a pound plus $29 for shipping and handling. Now, what does this imply? What it says is, look, one price is much cheaper than the other, but you've got to pay more to buy in. Let's see what happens, for example, if you only bought 1 pound. Using catalog A, you're paying $3 for that pound plus $2 for shipping and handling. That's in effect, you're paying $5 a pound. On the other hand, if you use catalog B, what happens is you're paying what? Only $2 for the pound, but you're also paying what? $29 for shipping and handling. So that 1 pound in effect is costing you $31. So obviously at that point, catalog A is a better deal than catalog B. But suppose you were buying 100 pounds. 3 times 100 is $3. The shipping and handling charge is only tacked on once, so you're paying that $2. You're now paying what? $302 for 100 pounds. Isn't that $3.02 a pound? Okay. Look what's happening with catalog B. You're paying what? $2 a pound. That's $200 plus the 29 is $229. So even with this big shipping charge, you're paying considerably less. In fact, do you notice what's starting to happen? The shipping charge gets sort of amortized over the price per pound if you buy enough pounds. Look what's happening over here. The catalog A is down to $3.02 a pound, which is pretty close to the $3, while catalog B is now down to $2.29, which is getting close to the $2. In fact, if we bought 1,000 pounds, look at what would be happening. See, 1,000 times 3 is 3,000, plus the $2 for shipping and handling is $3,002, which would come out to be what? 3,002 cents, 2/10 of a cent per pound. That's pretty close to $3 a pound. On the other hand, by using catalog B, 2 times 1,000 is 2,000, plus the $29 for shipping and handling would be $2,029 for the 1,000 pounds. That comes out to be what? 2,000 and a little bit less than 3 cents per pound. Now look what's happening algebraically. If you're buying X pounds, catalog A tells you the cost is going to be what? Multiply the number of pounds by 3 and add 2. That's 3x plus 2. Catalog B says multiply number of pounds by 2 and add 29. So for x pounds, you're paying 3x plus 2, okay, for catalog A, and 2x plus 29. And the equation 3x plus 2 equals 2x plus 29 simply says at what number of pounds will these two be equivalent. Now, you can solve this without algebra. See, what you can say is, look, every time I buy 1 pound at $2 a pound versus $3 a pound, I've saved $1. Now, here's a $29 shipping and handling charge. Here's a $2 shipping and handling charge. The difference is $27. I have to manage to save $27 before I get my money back. And at $1 a pound, how many pounds am I going to have to buy to break even? I just have to buy 27 pounds. You see, all you did with the algebra is when you, see, what was the equation that we had? 3x plus 2 equals 2x plus 29. When you subtracted 2x from both sides, you got this. Then when you subtracted 2 from both sides, you got this. And all the algebra did was give you an easier way to get the same answer. In other words, what I mean by easier, you didn't have to think of this thing in a logical way. You see, what this showed was that this was the equilibrium point, as we call it in economics. This was the price where everything broke even. What we're saying is that when you were buying just a few pounds, this was the better deal because even though you were paying more per pound, you weren't paying as much in shipping and handling. But beyond a certain number of pounds, the better deal was what? When you bought this one. And where was the break-even point? At 27. At 27 pounds, each of these methods would have cost you $83. Okay? And you can do this with any number that you want. For example, suppose it's $5 a pound versus $3 a pound. And the $5 a pound is $8 for shipping and handling, and the $3 a pound is $50 for shipping and handling. What's the logical way of doing this again? Every time you buy a pound at $3, you've saved $2 over buying at $5. You have to make up $42. At $2 a pound, to make up $42, you're going to have to buy 21 pounds. Let's check this out. At 21 pounds at $5 a pound, that's $1.05, plus the $8 for shipping and handling is $1.13. At $21 a pound, at 21 pounds at $3 a pound would be $63, plus the $50 for shipping and handling would also be $113. And if you wanted to solve that problem algebraically, all you're saying is that one way it's $5 per pound plus $8 for shipping and handling. See, the 5 is modifying the x, the 8 isn't. The other, so in other words, the x multiplies the number, the 5 multiplies the number of pounds, the $8 is just added on, and at $3 a pound plus $50 for shipping and handling, this side would be 3x plus 50. How do you solve this equation? Step 1, get the x's onto the same side. How are you going to do that? Subtract the smaller number of x's from both sides of the equation. Since 3 is less than 5, we subtract 3x from both sides. That leaves us with what? 2x plus 8 on this side and just a 50 on this side. To unblock the 2x, we subtract 8 from both sides, so 2x is 42. We then divide both sides by 2 and notice that we get the same answer. By the way, a topic that we will talk about later in the course, but I wanted to introduce again now, is the value of doing problems graphically. In other words, if we were to actually graph what's happening over here, you see, what we're saying is let's see, I want to make sure I get these stated right. The one that's $2 a pound, the one that's $2 a pound, starts out with a $50 shipping and handling charge. So in other words, you're paying $50 before you even get started. The other one that's more expensive, you're paying what? A lower amount at the beginning. The cheaper one is a lower amount. And okay, what I'm saying is I can draw the graph of how much it costs me to buy a certain number of pounds. Okay? When these two pictures are drawn, all I have to do for a given number of pounds is, let's suppose I want to see which is the better deal at $14, if I want to buy 14 pounds. I simply come over here and draw this line. And this tells me what? This height is the price at one price. This is the price at the other price. I can see that the red line represents a higher value than the black line. But what happens when we buy 21 pounds? the two lines crisscross. Notice that the line that was on top before shifts over to the bottom and vice versa. And in fact, where algebra comes in is simply what? If we start with the number of dollars and want to find out how many pounds we can buy. For example, suppose I want to buy, well, I don't care what number we want to buy. Suppose I want to buy 70 pounds. I come over to the 70, I want to spend $70. I come over to the 70 over here. That's the number of dollars. Okay? And I simply do what? Come over to here. And then from here, I come down to here. And that tells me what? Now, starting with here, I can work my way down to here. That will tell me how many pounds I could buy for $70. If I want to use the stuff that's cheaper, I simply do what? Come over to where that line meets over here and see what the price would be. The important thing is, what's interesting from the graphical point of view, is that the picture takes the place of all the math, and we're going to talk about that in more detail later. You see, arithmetic is when you start with the input, the horizontal value, go up to the curve, and find the output. Algebra is when you start with the output, come back to the curve, and come down and find the input, okay? Now, the important thing is, as we look at all this, that what we're going to be dealing with is we're starting out with linear equations. Linear equations are the building block of algebra. As we go on, we're going to find what? More and more complicated relationships. And as the relationships become more and more complicated, the technique for solving them is going to become more and more complicated. And the net result is going to be that more often than not, we're going to use the results of the graphing, the picture, to solve problems much easier pictorially than it is to solve them algebraically. In other words, reversing the steps to get from the output to the input algebraically is much more difficult than starting with the graph and looking from the vertical axis over to the curve down to the horizontal axis. These are all the building blocks that we're going to be using, but before we get to that, there's one more concept that we have to talk about in solving linear equations, and that's the situation where some strange things happen. It's conceivable that a linear equation doesn't even have any solution, and other linear equations have infinitely many solutions. And that's what I want to talk about next time. But until next time, let's just keep studying, learn a lot, and stay young. See you soon.